Okay, Andres, take it away.
Thank you. Okay, thank you, Melissa. Let's see. Okay, I'm sharing the right screen, correct? Yeah,
Yep, yes it is.
thank you. Welcome everyone to this session of the Ruin Data Academy, our second day. Hope you're having fun. We're gonna be talking about deep coadds and the object table. My name is Andres Plazas Malagon. I work for Slack National Accelerator Laboratory and I'm part of Rubin's community science team. Um, this year, the Rubin Data Academy is going to focus on beginner level use of the Rubin Science platform and access to Data Preview 1 data products. In the past, we've had some hack and networking sessions, but now we're having questions and answers sessions. So after this, there will be a Q&A session if you want to stay in this main room. We have 10 sessions for 10 topics that are repeated throughout the week. And we also have different times. Some in the morning. These are Pacific time shown here. We have some in the morning, some in the evening. Hopefully, they can overlap with other time zones to increase accessibility. I wanted to remind everyone about the community forum, the Ruin Community Forum. If you go to community.lsst.org, you can open an account for free. Even if you don't have data rights, you can open it. And the Ruin staff are here to help you. Anything related to RSP, to Ruin, DP1, in particular, if you go to a support category, if you open a topic, we're going to reply to that topic or find you the expert who can reply to your question. And at the same time, we encourage users, the community, to help each other in this forum. Um, then I also wanted to point out to the documentation that we have for this data preview, DP1. You can go if you go to dp1.lsst.io. All the information in this session is available there. There's gonna be a paper on data preview 1, but there is a current draft, so that paper is in internal review. It might change a little bit, but a current draft, it is public, so you can go to that website that is cited there. It's Ruin Technical Note 095, and it has a lot of detailed information on DP1. Each data set also has a digital object identifier, the LSST ComCam instrument used as well. So please cite that. And if you want to find general information about the Ruin Observatory, including how to cite the observatory, please go to rubinobservatory.org, go to the For Scientists section, and you're going to find all that information there as well. Today, we're going to show a few tutorials about deep coad images and object table, and hopefully we can make it through all of them. And the table contains photometry for these detected static sky sources. So we're going to talk about a little bit about data processing, image combination, detection, the blending measurement, the data products like the deep coad images and the object table. And we're gonna go quickly through some of these tutorials, most of them hopefully, two of them related to the portal aspect of the RSP and a couple of them are related to the notebook aspect of the RSP. We're going to start with some key concepts that we're going to find throughout this presentation and in general in Ruby and LSST. Some of them are sky map, tracked, and patch. So a sky map is an all-sky tessellation grid that subdivides the sky into polygonal tracks and patches. So the sky map used for DP1 has about 19,000 tracks, and each one covers roughly 2.8 square degrees of the sky. And each tract is further subdivided in 10 by 10 equally sized patches. And so each patch is about 0.028 square degrees. That's about 79 arc minutes by 79 arc minutes. Then another other important concepts are object and source, and the LSST uses specific definitions for these terms. A source is a detection in a single process visit image, and an object is an astrophysical object at a static sky coordinate. The source table contains measurements made of objects in a process visit image, and the object table contains measurements made on objects in the deep coordinate images. So how do we do this image combination for data processes in order to produce the deep coad images? The coadded images, they're created by combining multiple calibrated images obtained in the same filter and on the same region of the sky in order to achieve greater depth or sensitivity in order to increase the signal to noise ratio. So we do an initial cut on the inputs. So we only select processed and calibrated visit images with a scene of less than 1.7 R seconds, or PSF full width of half maximum less than 1.7 R seconds. We create masks in order to get rid of transients and artifacts such as satellites or cosmic rays, in order to exclude them from the final coadded image. Then we do a co-registration of these inputs. So we align all these inputs and we warp them into a consistent pixel grid. And we combine the image with a stacking algorithm, with a mean stacking algorithm that is weighted by an inverse variance. We do a residual background subtraction, which is a constant background residual is fit and subtracted, and we end up with these deep coadd images. Each coadd image then covers one single patch of the sky with a calibrated flux in nanojansky. So this is like the general process of how to produce these images. You can find more details in the DP1 paper. In order to do object detection and measurement. So a detection is something that has a signal to noise ratio greater than 5. These are any footprint in a deep coadd image gives us a detection. But then sometimes we have, many times, we have footprints with multiple peaks that are actually blended into child parent objects. So in particular, we use something called Scarlet Light, a software called Scarlet Light, which is a version of the Scarlet developing software from Melchior et al. 2018. Then we do for the force measurements. We use all deep coadd detections in at least one filter, and the coordinates are fixed in order to do these forced measurements, forced photometry or something like that. So we have PSF and extended objects fluxes. We do also shape and size measurements, and we do this in all the 6 photometric filters that we have. So as such, because it's force, almost by definition, the force measurements could have a signal to noise ratio less than 5. And then we end up with the object table. So on the right, we have a picture of the blended footprint, and that is going to be split into apparent and children. So the deep coadd images, we access them in several ways. We can use the bottler. We recommend to access images in the notebook to use the bottler. But we also have a couple of protocols from the International Virtual Observatory Alliance, which are simple image access and table access protocol. These are services that you can use in order to access the images. For example, for the bottler, you need to give the bottler the minimum amount of information in order to retrieve a deep coadd. So you give it the name of the data product, and then you give it the band, the photometric band, the sky map, the tract, and the patch. And then it also is also a particular type. Exposure F is a particular type of internal type of the image. If you're gonna use the services from IVOA, you can use, as I said, SIA and TAP. These are what is called calibration level 3. This is some language from IVOA. Very briefly, level 1 is ROS, level 2 is visit images, and the rest is like a coadd is level 3. So for DP1, we're gonna have about 2,644 images. And the pixel data, each coadd image is their 2-dimensional arrays. So these exposure Fs, they have like 3 planes. One plane is the image plane, which is the sky pixel data in units of nanojanskin. The variance plane, which is the uncertainty, the noise in the flux in units of nanojanskins squared. And we're gonna have a mask plane, which has an integer bit mask of flag values. They're similar to what was used for the SDSS bit masks. We also have a list of metadata with the list of input images for each one of these coadded images has this information, the PSF function associated to it, photometric calibration, and the astrometric solution, the world coordinate system. You can look at the schema for each table. You can go to this website, SDM schema-schemas.lsst.io, or also the portal aspect of the ISP, the user interface. It can also contain the schema. For the object table, we have something similar. We can access them again via the services, the tab service of the butler. We recommend using the tab services for accessing the tables. We have the necessary dimensions if you're gonna use the butler, but we have the name in the tab service. We have the particular name that we need to use. Something of notice is that we're gonna have about 1,300 columns. That's a lot, so it's good that you specify the columns that you want when you do a query, either in the butler or in the tab service. And we're gonna have about 2,003,300,000 rows for DP1. So imagine what we're gonna get for LSST. So we're gonna have different, so because we have so many columns, there are some of them that are key columns, like the object ID, the coordinates, the fluxes, magnitudes, some shapes, and other flags in order to do different cuts. So one of the first things that we wanted to show you is how to look at an image in the portal. So maybe we can, but we're going to, let me see, let me go back again to this query. We're gonna actually use an ADQL query in order to retrieve a deep coad image that overlap the center of one of the fields, the Chandra field, like the deepest one observed in DP1 campaign, the extended the Chandra deep field south. So notice that we're gonna get this up score is the one that's gonna give us the images, but you notice here that the constraint has the Calib level 3. And also we give an extra constraint about the image. And we also give another constraint for the data product subtype, we have deep coad from LSST, and we're gonna retrieve a region around the center of the field. So here, if you can follow along as well, I'm gonna just copy paste this. I'm gonna go to the portal aspect of the RSP. This is what shows up. First, when you open it, then you can go to DP1 images. You find a user interface here that it's also nice and helpful, and you can do whatever selection you want to do here. But in this case, we're gonna go here to the upper right corner. Let me see again if I increase a little bit the size of my screen. We go to edit ADQL. You have examples here. If you want to take a look at that, they're already pre-filled. But that query that I just copied from the slides, I can paste them there. Then I go to the lower left right before the, sorry, lower left corner. Before that, I wanted to show you the schema here on the left. Here, you can look at the different schemas. So I'm not gonna open that right now, but just to let you know what it is. And go back to our exercise. We do search after we do the query. And then it just works. Great, thanks. So there we have a lot of tutorials about the portal. I'm not gonna go a lot in detail here, but there's a lot of cool stuff that you can do. You can change the layout for this here. You have like the columns that you have. You can change the layout of here if you go to this burger thingy on the upper left. Results layout. I only want images and charts, for example. That's one thing you can do. But then let's just put it back how it was. Image and some tables. Okay. And then you can add like coordinates here and explore. And that's a lot of cool stuff that you can do here with this. So just to maybe whet your appetite. Okay, so that's one query. I think we have a lot of stuff to cover here. But that shows us the image. If I want to get rid of the coordinate, I can do this. I can go to one of these. Click here. Click here. Okay. All right, so that shows us one of the coadded images here on the left. Then if we want to now retrieve some objects that are near the center of this field, now we're going to look at the object table. So again, this is an ADQL query. We're going to get some quantities of interest, like some coordinates, some magnitudes, composite model or PSF magnitudes from PSF fitting, composite model from SDSS. Again, we do a constraint, a circle of a certain radius around the center here. And we do another cut in magnitude in order to get something smaller and more reasonable. So we're gonna copy the query again, Just notice again that we're querying from the dp1.object table. And in this case, or before, for this one, we went to the images because we were getting images. Now we can go here to catalogs. We have a similar interface here, user interface, where we go again here to the ADQL query. We paste it and we search, and let's see what happens. You can monitor your jobs if you want, I guess. Let's see, job monitor, completed, data. Okay. So we see here some of the objects that we queried around the center. We can do a zoom in, and that's pretty cool. Okay, this is what we got around the center, some of the columns here. We can go, for example, to the chart here. It gives you a details. There's a tab here that shows us a little bit of explanation of what actually we got with some definition from the schema. But in this chart on the upper right, you can, in this case, by default, it's just plotting the coordinates. But you go to this, I forgot to say this in English, this engine icon, gear icon, and you can do whatever you order it to retrieve. You can, I don't know, you can do GC model minus, you can do some color magnitude diagram, for example. And it's in red because it knows that I made a mistake. I think, let's see. Oh, what am I doing wrong?
The underscore.
Thank you. Greg is our expert. And this is a cool thing because he was in red because he knew, no, you're wrong, but now he's not. Actually, I want to put this in the y-axis and then okay, let's just do that. We can move this with this little hand and then it gives us some version of a color magnitude diagram. But that's just a very quick illustration of what you can do. Okay, I wanted to show that from the portal, but at the same time, I know this was very fast, but we're recording this, but we have tutorials on the portal. So I invite you to encourage you to explore at your own pace. And of course, you can always ask us questions in community. But here, I also wanted to go through a couple of the notebook aspect tutorials. So if I go to the RSP again, data.lsc.cloud, then I go to the notebook aspect instead of going to the portal aspect. And then one cool thing is that you go to this tab here at the top, tutorials, we go to DP1. In this case, I wanted to tell you about the object, the coadded images. So we go to data products, images, deep coadded. And yes, overwrite, because I was already looking at it, that's fine. So we're gonna take a look at this tutorial. So we start by learning, talking a little bit about the learning objective, the type of products that we will use, some credits and how to get support. All our tutorials look the same because we follow the same guidelines and the same style. But in this case, we're gonna talk about the deep coadd. So this is, as I was saying, I'm gonna repeat some of the information that I was saying in the presentation, but this is a combination of multiple processed and calibrated background subtracted images for a particular patch of the sky for a particular LSST filter. The data set, the name is deep_coadd. We have 2,644 of those. There are some related tutorials for that. We start importing the relevant packages, in particular the bottler. We're going to retrieve an image, so we recommend using the bottler, and we're going to display it with Firefly, which is something that looks very similar to the portal you will see. So we start by defining the bottler with our data set, DP1, the particular collections for this. We're going to tell it that we want to use Firefly. You'll see what that means in a second. And as I was mentioning before, it is recommended to use the data butler to retrieve images, although they're also available via the tab and the simple image access services from the IVOA. So the butler, as I was telling you before, it can show us the dimensions that are needed for this particular data product. If you had this function get dataset type, we give it the name that we already put there. And it's showing us that it's a type of a format, the exposure F format that has those three planes that I was telling you about before. Here, I was mentioning that there are dimensions there is the minimum amount of information that you require in order to retrieve these objects, and then it's telling you need to give me a band, a sky map, a tract, and a patch. So we're gonna do a demo query. We're gonna define the central coordinate around the Chandra field in the R band. We're gonna define this little query here that is similar to what we're doing with SQL, and we're gonna get the data sets, the references affiliated or associated with those particular constraints. So here in this case, I was mentioning before, one patch is one coad image, but here we're getting two. It's just telling us that the patches overlap because tracks and patches do overlap. The sky map is a tessellation, they're disjoint, but the tracks and patch do overlap a little bit. So in this case, we have the center of the field happens to be in this overlap region. Then in order to get the image, we have several options. We recommend using the butler. We also can with the butler here with the butler. Sorry, we can pass these data set references that we got here when we did query data sets, or we can explicitly pass the data ID or the tract or the patch directly. So we're gonna take a look at how we do it in the first. We got two of those references. We're gonna get just one, the first one, and would you just pass that reference to bottle.get to get the deep coad, then it's showing us that it's of type exposure F. And then we're gonna take a look at what it looks like in Firefly. So it's actually not opening Firefly, so I don't know if I need to open it here. Is it open it here or what? Let me see, because it should be opening another Firefly window. Let's try something again. Vamos a interrupt the kernel. This always happens. That's fine. A live demo. Let's try it again because I was playing a little bit with this before. So let's see if when we define the backend, then now it shows up. So there was something going on, so I just killed the kernel and started again. And then it does have some information from before, but that's fine. Let's see. So again, let's retrieve. Let's do the butter. We already did this, and display. Well, still getting here. Okay, I guess that's the image that I wanted to show because as I said before, I was playing a little bit with this, but you can see it does resemble. It's the same as the portal aspect. And okay, cool. So let's clean up a little bit. You can use also with the butler, you can also pass data ID. The references can give you this data ID and it has the information that you need. Your band, your sky map, the track, and the patch. And you can also just do that with the butler as well. In this case, you do deep coadd, you do data ID, and you pass the data ID that we retrieve. That's another way of retrieving it, of retrieving. We're not gonna, it should show the same, but I'm not gonna display it. Or you can directly get the band, the track, and patch numbers. And in this example, it might be redundant. Of course, we have all this information, but in another situation, it could be that you got the track and patch numbers from somewhere else, I guess maybe using the SIA or the tab service or somewhere else, and you just have that information and just wanted to show you that you can pass that directly. So as I was saying before, here from the references, we can just individually get the band. From the data ID, we can get the band, the track, and the patch. And you can just pass that explicitly to the butler. But just in case you got that information independently from something else, that's another way of getting the deep coadd. So that's how you get this object. We can do a little bit cleaning here. This is just some explanation that you can go to, if you go, for example, to the portal aspect, you can also access this type of images using these two services, the simple image access and the tab service. Just keep in mind that if you want the deep coadd, this is a calibration level 3 product in the language of IBOA, and the DP subtag, which is something that we already did before. Then this is something similar, but for the table access protocol as well. We do have tutorials on how to do this as well, in addition to the queries that I showed before. So we're gonna go through that and we're gonna analyze a little bit the object that we just retrieved, the deep coadd image, which is an exposure F, and as I was mentioning before, it should have 3 planes. So the image, the variance, and the mask plane. Okay, so we're gonna take a look at the deep coadd image. In the frame number 1, you can open different frames in Firefly Viewer. And okay, automatically it should have the mask there, but you can control that with the display of the mask with this set mask transparency parameter here. So in this case, before we were doing like 100 transparency, so fully transparent in one of these commands here above. So that's why we didn't see the mask. But here now we're putting 0. So we're telling it, please show us the mask. And then it gives us the mask. So this is a screenshot of that. And it should look like this in the real-time demonstration, which it does. So that's good. We'll talk a little bit more about the masks later. You can also get the image plane, just the image plane, which has the sky pixel data units in units of nanojansky. And you can get here, this is a typo here, but it says you can get the image from the deep coadd image, not the visit image, but the visit image has something analogous as well. But in this case, there is a method. All these objects, you can play around with them, and then it has all these cool methods. In particular, also, you can just get a NumPy array from the image. You can take a look at the difference of the two objects that you just got. The image, it's more like something called astronomy framework, like some LSST science pipelines class, this object, which includes the pixel data. But if you just get the array, you just get a NumPy array, which is this. But that's just showing you can play around with it. You can, using the array, then you can just start using the standard NumPy methods, for example, to get some statistics. And then we can open a frame number to a different frame in the Firefly viewer and display the image. So here we pass the frame here. So we preserve the one that we had already opened. And once we run the cell, then it shows us the image. Okay, something, a subtlety here is that here we're telling Firefly to plot the image, which is just a NumPy array. So it doesn't know anything about the astrometric solution, which is the mapping between pixels and celestial coordinates. So here on the right, if you move the cursor a little bit, you see that this is in pixel coordinates. But before we were plotting the whole exposure F object that has all the information, the deep coad. So it does know about the WCS. So Firefly is using that information in order to get you sky coordinates here on the left. And if you move the mouse, you can see the cursor, you can see the celestial coordinates there. Okay, so that was for the image plane. You can also take a look at the variance plane. Then again, the deep coad, it already has all that we need. We do something analogous to what we just did before, getting the variance, and then moreover, just getting a NumPy array from the variance in order to do some statistics. We can open yet another frame in Firefly just to preserve the work that we have so far. And then it's giving us here, sorry. Let me see. Here on the right is giving us the variance plane. So you can see the correlation then with noise and the celestial objects. So the third plane that this type of objects have is the mass plane. It has bit values, similar to what was used in the SDSS bit masks. We do something, again, very similar, very intuitive as well. The deep coad object, get mask, we get the array as well. Here we can print a list of the objects. I'm sorry, a list of the masks of the names and the bits and the colors that that Firefly will use to display them. So yeah, here we have the name, bat, clip pixels, cosmic ray, crosstalk. Then in parentheses we have I guess the binary representation. So you will see you take 2 to the seer. In the end, every single pixel has at least one or a combination of these masks. And the way it's represented is that you take, if this is in base 2, then you take 2 to this exponent, and then if it has more than one of these flags, then you add that number, and then we'll see how we get a final mass per pixel. So I'll explain a little bit more about that later. But we can show the image here in another frame. Which is here. Let me try. Okay. Just changing a little bit here the zoom. I still want to preserve all the images. We're gonna have like different colors as the notebook explains that Firefly is interpreting these mask colors as flux values. But we can change that again. Where are you? Where are you? Where are you? Okay. Two. Okay. If we set the mass transparency to 1, I'm sorry, to 0, then we're gonna have the same colors that we got before in frame number 1. So that's just what this cell is explaining to us. But if you wanna set, for example, all mass key names to transparent except the detected one, then you can first set all of them to 100 transparent, and then you can just put the detected one to opaque, which is 0. And then you see the detected flag. And those are the objects that were detected. And then, as I was saying before, you can print the unique values per pixel. These are all the mask values, and the number of pixels that you count in the number of pixels that have those values. In this case, as I was saying, for example, we have cosmic rays and interpolation, and the number of the mask is 12. So 12 is the value of cosmic ray plus of interpolation, which is the value of cosmic ray is 3. So that's 2 to the 3 plus 2 to the 2. So that gives us 12, 8 plus 4. So that's why it gets 12. And then of course, can imagine it gets a little bit more complicated with here, but there are standard algorithms to just get back the the bits that you want. Okay, so let's move on. We can keep exploring the metadata. You can think of metadata as the header of a fits image, more or less. That's the equivalent. And then again, the same deep coad object is gonna give us metadata through this method called get metadata. You can take a look at it. As I was mentioning before, it kind of looks like a fits header. We can put it in a different format, a dictionary. For example, if we want to query a particular string or regular expression, like the unit, is there a string that has units? Yes, there is. This is the keyword. And if we just look at the value, it's telling us this is in Nanojansky. So that's one example of looking at metadata. Let's do some cleanup here. We can keep going and exploring and poking this object, the deep coad object, and it has another handy function that is called get info, like general information. And sometimes you're interested in the inputs that went into producing a particular coad. So you can use get coad inputs from that info. You get first the info, then info has get coad inputs, and then you can get a list of the visits and detectors as AstroPy tables that went to those to form that coad. So you can take a look at it. I guess here is a table. Take a look at the visit ID, and these are the different visits that went into it. So that's also handy and useful. Another useful property is that it has a coad has its astrometric solution or world coordinate system. You do get WCS, and then it tells you about the pixel origin. It tells you about the plate scale at the center of the field. There is a subtlety here that if you call if you call calculate the pixel scale in a different part of the focal plane, it might change a little bit. And I do believe we have a tutorial about that. But in general, the plate scale is 0.2 arcseconds per pixel. So you can just convert coordinates from pixel coordinates to sky coordinates and vice versa using tools from the LSST science pipelines. You need to just define the appropriate objects with the appropriate units and use something like some of the methods from the WCS object. In this particular case, a sky to pixel object. So we do have a tutorial about astrometry as well that shows you a little bit more about this, how to work with the WCS. We can get the bounding boxes of the coad. Again, we can define the corners of the coad in the different using different objects from the lsst.geom package. You define them as two-dimensional points, but then this get box has methods to know the end and the beginning in each one of the axes, and then again you can use the WCS to go from the coordinates in pixels for the corners to coordinates to celestial coordinates, and then you know the area of what you're looking at. You can take a look at the area. You do a little bit of math, and then you calculate it in units of a square pixels of a square arc minutes, and you can also take a look if certain values are within the box. It has a contains method, so you see that it's very intuitive, object-oriented, and you can poke each one of these objects, and it has very handy utility functions. Okay, here we checked if a certain pixel is within this region in pixels, and here we'll checking if a certain point is within the sky coordinates, again using the WCS as well. Okay, so that's pretty cool. We also have the PSF model, the point spread function model. I don't know if I was saying before that it was derived with using the PIF software, PSF in the full field of view software. Okay, but then in a very similar way to the deep coad, we do get PSF at different coordinates here. We actually do, this cell is actually showing us what it looks like if we go in a different frame. Is this little tiny postage tab here. All right, that model looks symmetric and nice, but yeah, looks cool. It's a coadded model. And you can also calculate the shape of the PSF, you determinant radius, you can calculate, well, this sigma, the determinant radius gives us a sigma for the PSF, and you can convert that to full width of half maximum using the conversion constant. And then it just gives us the different quantities that are related to the morphology and the size and the ellipticity of the PSF. That's usually useful information to know. In this particular case, I believe is using HSM moments or Hirata, celiac, and Mandelbaum moments. Then for the detect objects, okay. So in general, the tab service is the recommended access mechanism for catalog data, as I was saying before. But sometimes there are cases in which all the objects that, or if you have a visit image, all the sources in a given image they are required, then sometimes the bottler gives you a better, a quicker way of retrieving them. So in this case, we're going to show an example of that. We're going to get the tract and the patch for the coadd using the dataset references that we obtained before. Then again, showing the dimensions, the dimension that is required for the object dataset here is the tract. And then we're gonna do a query. We're gonna use again, the bottler to query the object table. And as I mentioned before, this table has like 1,300 columns, so it's way more efficient if you just know, hopefully in advance, what you wanna get, and you define that in a list of strings and pass it to the bottler parameters, this dictionary. This keyword parameters has a dictionary that has one keyword called columns, and then you pass that. You pass your tract, and I didn't define it because I should have run this cell before. Okay, then you get everything here, and then if you need to do further filtering, then it's your job maybe to do some filtering here. If you just want for a particular patch, because you got everything for all the patches from that tract, then you can just do a filtering here. And then you can take a look at the table here. Um, okay, so then we can redisplay the deep coat in frame number 1 with no masks here. Let's see. There you go. Voila. And now we can overplot the sources that we got. So we were doing some cleaning here because we want to overplot the sources in orange. And these are the sources that we got from that object table, overplotted on the coat. Okay, so I think that's it. I have technically 5 minutes, so I don't think I have time to go through the other tutorial. Another relevant tutorial is the object table tutorial. But I encourage you to go over it, and maybe I'll just go over it in the next session if you maybe wanna do come to the other session. But we're recording this session, so it's fine. I think I have a few minutes for questions if you want to. We're also gonna have a new another Q&A session afterwards in about 15 minutes. So feel free to just disconnect and come back. But I think that's what I wanted to display for today related to this. Hopefully it was useful. As always, we welcome your questions in community. And right now, I have 5 minutes, or in the Q&A session in 15 minutes. Okay, thank you. So I don't know if anybody has any questions. I'm just looking at the chat. Lots of activity. Thank you to my CST friends and colleagues for looking at the chat and answering your questions. I don't see any raised hands or anything like that, so that's fine. So we can see you later or ask us questions in the community.